Okay, welcome everyone. Today we're delighted to have Neal Weiner visiting from NYU. Neal and I go way back. Yeah, we were grad students at Berkeley in the 90s, around the same time. And then in 2006, I was interested in the excess 511 keV photons seen by integral, and I called up Neal one day and said, I'm about to waste a lot of your time. And kind of pitched an idea, and he thought about it for 3 days and came back with a model that I think was totally wrong, but then it reiterated. And wasted many years, actually. Wrote about a dozen papers. Came up with a beautiful idea of how dark matter could be, which is not how it is. Maybe. But then, yeah, there's recent stuff. Anyway, but that's not what this talk is about. Yeah. So Neal has worked on other things. He is a particle physicist who really cares about the astrophysics. He's worked on trying to kind of perturb the standard model of particle physics in ways that will help us explain things seen in the CMB or in James Webb or lots of other things. Today he's going to tell us about his little red dots. I said, well, Neal, you can come and as long as they aren't contagious, you can come and talk to us about your little red dots at the Redshift frontier. So,
thank you for very, very interesting introduction. I expect nothing less from Doug. Doug actually hosted me as a graduate student, prospective graduate student at Berkeley when I was looking at places, and I decided to come in spite of that. But we had a great time thinking about all sorts of models, which I'm not going to talk to you about today. Today, I want to talk with the title, Particle Physics of the Redshift Frontier. I'm a particle physicist. You don't get a lot of particle physicists here. I understand that. But particle physics and astrophysics have had an incredibly, tremendously successful collaboration over now a century, really, in understanding things about the nature of the particles that make up the universe by looking at small and large structures in the universe. And so as new data sets have been coming online, it's always worth asking the question what the lessons are that we can tell each other from them. And so right now, obviously, JWST is an incredibly exciting thing for astrophysics. And from my perspective, it's also becoming an increasingly exciting thing for particle physics. And that's kind of what I want to talk about today. So before I go any further, let me just quickly introduce my collaborators, especially with regard to the little red dots work that was really done almost entirely by Wenzer Chin, who's you will come to know next year when she's on your short list. She's a Simons Junior Fellow at NYU and has CCA affiliation as well. Shobik was an NYU postdoc. He's now at Tufts. A lot of the ideas about modifying inflation and changes to inflation that I'll talk about today actually originate in his work, and he was really the origin of those ideas. So he's just, I don't know, up the street, down the street, across the street somewhere. I don't know what the geography of Boston is, but he's nearby, and so I encourage you to get to know him. And of course, Priya Natarajan, who probably many of you know, who's done very, very influential work on black holes that helped inform our particle physics ideas. So let me start with a disclaimer. Like I said, I'm a particle physicist, so sometimes my units will not make sense. We like to work in natural units. We set h bar equal to c equal to 1, so we don't have to use things like time. That means that sometimes I will say something like, this occurred when the universe was only 10 to the 25 inverse joules old, so I apologize if I slip into that. On the other hand, I don't think that you guys should be throwing any stones right now. This is only going to be relevant one time. I'll try and highlight that. And the rest of the time, I'll try to use good units. That said, I do want to just point out that Hubble at around 70 kilometers per second per megaparsec is actually just a rate if you cancel out the dimensionful length units, okay? So, but I'll put that aside for now. So my kind of starting point, I was at a workshop at CERN over the summer, and there was a postdoc, Rudin, Petrosian Byrne, who kind of raised this big question for everybody. If you are a beyond the standard model prone person, which is what I am, somebody who's interested in physics beyond the standard model, what should you be thinking about and why? And at least one answer for me, as I was thinking about this, is trying to think about JWST and how that can be relevant for us. So the question is why? Or another way to say it is, why is a particle physicist at the Center for Astrophysics giving a colloquium at all? Well, one really good answer is if you go and you just go to a standard particle physics talk, they look like this, right? So you get blah, 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 and you get to the end, and then the particle physicist says, isn't that amazing? Isn't that amazing? And then on the other hand, you go to the astrophysics talk, and it looks like this. And we're a little jealous. And so I wanted some opportunities to have more talks like this and have a point where I could be like, look at these great images. So that's one good, maybe not the most important, but nonetheless good reason why I think this is something particle physics should do. But there's a second reason. And that is that JWST is probing a new regime of cosmic history in a way that's never been explored before. And that when you think about what's going into what JWST is seeing, namely, the early structures and how they manifest themselves, obviously through stars and other ingredients, but still we know that physics beyond the standard model, or BSM physics as we like to call it, so that is the properties of dark matter, the primordial perturbations that seeded all the structure we have, so that's sort of our purview, right? The origin of those things and the nature of those things. And we know that those are fundamental ingredients for what's going on in the JWST data. So, to the extent that there are deviations from lambda CDM, it's at least worth exploring the question as to whether they might appear at a redshift of 10 in a way which is somehow obscured at a redshift of around 0. And irrespective, this is a new and unique testing ground for physics beyond the standard model. I think we're finding that more and more. So the question is then how and what? So how a particle physicist addresses questions in astrophysics and how an astrophysicist addresses questions in astrophysics, I think are different. And I actually think that the astrophysicist has a much, much harder job here. Because if you go and you talk to astrophysicists, it's usually like, how do I understand the standard model well enough to know if I understand the things that I'm seeing out there, right? If I start with lambda CDM, there's a tremendous amount of very, very complicated physics that goes into just knowing whether or not the observations that are going on are consistent with that. There are many parameters, a lot of things you have to model. It's a very, very hard, question. And so to me, particle physics in some sense is a lot easier because there are many things which are not the standard model that we are interested in. And so we can at least ask the question, is there some limit of these scenarios where the signals of them would be so significant that I would not be able to ignore its implications? It would be so far away from the standard prediction that it would just stick out, right? And then somewhere in between those, you get hard questions where you're trying to distinguish between these things. But that basic fact that a particle physicist can say, I can start with something and just ask, is this something which I can test at all? Because I just want to know if that's a possibility. Kind of honestly lowers the thresholds of what is considered an interesting question and makes it something easier to ask, because you can basically just lower your standards until it's something you can answer. So with that in mind, we have our particle physics hat on. We watch the news come in about all these great JWST observations. So we're watching 2022. Early galaxies from JWST are breaking cosmology. I mean, of course, you're going to get excited about that, right? Then, in 2026, little red dots are out there. It could be baby black holes. And you go into this Scientific American article, and it says that these little red dots were also breaking cosmology. So cosmology is just being broken. And that's, for a particle physicist, that's great. It's like, you're like, what? So you have to ask this question, are we in a crisis of cosmology? And I, of course, answer this question the way anybody answers a question these days. I search it on the internet. And so this is what I found when I looked at the frequency of cosmology crises as a function of time. We had a crisis in about 2012, which I think is when the Planck data became sort of first inconsistent with the Hubble from local Hughes measurements. Then I think 2019 is when that became 5 sigma. This is some combination of these early galaxies in James Webb and DESI. And then I would say if you look where we are right now, looks like there might be the start of a crisis. So I'm being glib, but I'm just saying that there are questions that appear, and it's an open idea as these new data come in, whether they're understood with the standard model or not. And from my perspective, and this is where I now maybe start taking sides on things, is that I think it's important that we don't just assert that we understand what's going on in JWST. So the two phenomena that I'm going to really be focusing on as possible tests of physics beyond the standard model are these early massive galaxies in JWST and these little red dots that have shown up in JWST. And so, especially as you kind of read the literature, you'll see a lot of people saying well, I think that we can maybe get, we can get the star formation, we can get the things that we need to understand these early massive galaxies. And it's important to distinguish, there's the question about whether we can get them in lambda CDM or whether we necessarily are a prediction of lambda CDM. And those are different questions. And the real difference between science, which we're all scientists, and the kinds of things that I like to tell my kids before I put them to bed is fundamentally data, right? And whether the story versus a nice story you can tell about something versus whether something is true is whether or not you have predictions that can actually test it. And I at least feel like we're at a point now where people are putting out predictions, and it's time for particle physicists to put out predictions too as to what kinds of things you can look for that hopefully as more data come in, we can test these things. The same thing is true in thinking about these little red dots. This is actually has a local author. A paper came out just like a couple weeks ago arguing that there's these phenomena of the little red dots that I will also come back to, indicating that these little red dots are very, very likely very heavy black hole seeds in the early universe that are sort of ubiquitously spread and accreting, and that's what we're witnessing. So then you can ask the question, well, do we really, in lambda CDM, understand where those seeds are coming from, or is that suggesting physics beyond the standard model? And I think we're at a point where it's still worth entertaining those possibilities and looking for what predictions there might be. So in case you fall asleep, you OD on the carbs in the back, and you pass out, my conclusion is that there are very simple particle physics scenarios that modify primordial perturbations that lead to early massive galaxies consistent with what's observed, large population of direct collapse black holes, and thus little red dots, and this is a little early because we're still working on this, but testable predictions, right? Things that you can actually go look for that can tell you if these things are correct. So when we're thinking about what kinds of things particle physics can motivate that are going to show up in these data, I kind of would group them into sort of two categories. One is the physics of inflation, so what's going to feed in and give you modifications to your real primordial power spectrum, the primordial perturbations that you were actually just given with at the beginning. And then there's also physics of the transfer function, so physics after those perturbations, so these would be like dark matter interactions that can modify the properties of those perturbations as they evolve throughout cosmic history. Talking about both these things in one talk is I think, a bad idea. I'm going to be focusing on the first today, but there's lots of interesting things to talk about in the second as well. So probably everybody has in this room has heard about inflation, but it doesn't mean that you necessarily have thought about it in the same particle physics way that I think about it. So let me take a little bit of time to sort of talk about inflation in the way that I think about inflation, because it will be relevant for some things later. So what do we know about inflation? Inflation is this early period of the universe when it expands superluminally. It expands by many, many, many orders of magnitude, at least e to the 60 factor of size to explain the phenomena that we observe. And in basically all kinds of models that function, it's driven by some scalar field that we call the inflaton that has some energy. So this is my inflaton, right? And it has some potential energy. And the energy density in that potential is what's driving the expansion of the universe. Now, because this is a potential, the inflaton field rolls down. So it slowly, gradually drifts down its potential farther and farther until some point where the energy density is not capable of driving inflation anymore. Inflation ends, the field continues to roll, and it deposits its energy into the rest of the universe. And so this is the model of how you should think, and I would like you to think about inflation as that there's some period, this whole time here, the universe is expanding, but the universe is not exactly the same throughout all this period because the inflaton is slowly drifting down this field. So the inflaton is giving you a little clock that's telling you how long this stuff is progressing, and eventually it hits midnight and inflation ends. And so a lot of the questions about the properties of inflation involve what's going on as this field is sort of slowly rolling down. A very important point is if you were to live during inflation, if you were an observer existing in that period of time, you would be limited to a region of the universe that you could see. You would be in causal contact. The universe would be expanding at some rate set by whatever the Hubble parameter is then. And like I said, the Hubble parameter is a rate. And so the inverse of that is a time. And so c times that gives you some distance scale. And so if you're an observer during the period of inflation, the universe might be huge, but you're limited in what you're in causal contact with some very, very small amount of that overall time, space. So how does that work? It works, here we start with inflation over here at this top of the potential, and this dot here, that's the entirety of the universe that you're capable of seeing as an observer in that universe, okay? So let me do that over here. So here's the inflation, you're living inside this dot, and that's as far as you can see. Then the universe expands really a lot because it's inflation. And so that original dot, as this field rolls down, that original dot has now grown to a much, much larger size. It's, say, doubled in size, okay? But you're still limited in how far you can see. So now you live in one of these green dots, and now that's as far as you can see at this point. So back here, you could see that whole region, but now that has expanded. You're no longer in causal contact with that whole region, and you only get to see what's in this little dot going forward. Then it continues to roll. Well, that original region continues to get larger. This green region also gets larger, and now you live in one of these red dots. So sure, you were in contact earlier with that whole region, and then you were in contact with that green region, but now you can only see this red region. And this continues to proceed, that the region that you get to see and interact with continues to stay fixed, but the regions that you were interacting with continue to grow and get larger and larger. So the different periods of inflation, as you're kind of proceeding, continue to expand. So why is that relevant? Well, why is that relevant is that this distance scale expands and today corresponds to some physical size in the universe, okay? So I'm just picking some sizes. Obviously, the universe is much bigger than 4 megaparsecs. But that this original size that I was hanging out with has now expanded. And maybe that region today, when I look out, is a 4 megaparsec region. And then these green regions have expanded and they're, say, 2 megaparsecs, and then the red ones are 1 megaparsec, and so on. So the very important point here is that different points in the history of inflation ultimately get mapped onto physical scales in the universe today. Okay. And that means that if we're talking about things that might happen during inflation, those things should be imprinted in some non-trivial way on specific distance scales when we look at the universe today. Now, when we talk about inflation, we usually like to talk about it in this way, right? We come up, we say there's some field, it's rolling down a plane, it's all very simple. There's some energy density from it being up some potential energy that's coming, it's transferring into kinetic energy as it's rolling down. But in reality, we don't know that. Inflation could be much, much more complicated, or the dynamics, at least, of this field can be much, much more complicated. And all we really know is that there is some stretch of this incline that looks like this. There must be some stretch which is nice and orderly, but it doesn't have to be nice and simple the whole time because we simply haven't observed perturbations at all scales. So one thing that people will say is, how do perturbations, right? People will say, inflation explains the origin of perturbations that we see, these 10 to the minus 5 fluctuations in the CMB and in the matter field that then grow and give us the structure that we observe. So where do they come from in inflation? Well, in inflation, because the universe is in a state of high energy, there are quantum processes that become very relevant. And so one quantum process that can happen is that this field can jump backwards. It can also jump forwards, but it can jump backwards a little bit. So on average, it's rolling down, but maybe it jumps back a little bit. And what's going to happen now is that since it's jumped back a little bit, if it so jumps back at one spot, one horizon, it jumps back a little bit, then that spot where it jumped back a little bit is going to have to roll even farther before inflation ends. And if it has inflation ends a bit later, that actually means that that's going to be a hotter region of the universe. So if I have some patch of the universe here where the inflaton jumps backwards, then it has to roll farther. That means that there's less expansion after the end of inflation, which means there's less dilution, which means that spot ends up hotter. If over here the field jumps forward, then inflation will end a little bit earlier there, which means there's more dilution after the inflation, which means that that spot is a little bit colder or lower density. Now, the physics of it is not so important for our purposes, except to say that as this field is jumping forward and backwards, those little jumps get imprinted as corrections to the overall density field of the universe. And you can go through sort of a twiddly estimate of it and ask what kinds of delta rho over rho do you get. You go through it, yada, yada, yada. And the important thing at the end of the day is you get an expression that looks like this, where you have v prime in the denominator. V prime, this is our potential. V prime is the slope of that potential. And so what this is saying is that as your potential becomes flatter, then the perturbations become larger. Okay? And this is the only reason that I'm bringing this up, is just to emphasize that when we go out and we observe the universe and we say, aha, I see 10 to the minus 5 fluctuations in the CMB or in the primordial amplitude of fluctuations for dark matter, those perturbations in inflation are related to the flatness of the potential. If you want 10 to the minus 5, you're basically making a statement as to how flat you want your potential to be. If your potential were steeper, then your potentials would be smaller. And if your potential is flatter, your amplitude of your perturbations would be larger. So the two takeaways that I want you to have about this that really I think are worth just remembering, you can forget about all the physics, is that as the inflaton, this field, rolls down its potential, different eras of inflation are imprinted on different physical scales that we observe today, and that the size of inflationary perturbations are fundamentally connected to the flatness of the inflaton potential. So we've observed, we know already in physics that there's 10 to the 8 range of scales that have already been observed in various astrophysical settings, and we believe those perturbations go down to regions that we have not observed. And so all you need to believe to imagine something interesting happening is that maybe somewhere along there, this potential is not the same slope as it is over, a billion, a factor of a billion in scales. So there are two basic scenarios that I'm going to consider, and they look like this. So we take that inflaton potential, and then these are the sort of like two possibilities. One is inflation looks more or less ordinary. The ball can roll down the slope, but there are sort of like weird things creeping just outside the inflation that can kind of play a little bit of a havoc as it's coming down. Or one where the inflaton is rolling normally here and it's rolling normally here, but the slopes are different. Okay? Those are the two scenarios that I'm going to want to consider. We'll start with the monsters one. And the question here is sort of stepping back and asking a general question. What if random, rare things happen during inflation as it proceeds? Okay? We already know that there's perturbations from inflation that modify things that we can see. What if there are random, strange things that also occur? Well, this is why I now want to step back and talk about the early massive galaxies. So I'm sure you've seen hundreds of talks about early massive galaxies, or at least tens. I was first learned about this by Mike Boylan-Colkin talking about this at a particle physics conference, and he was like, you guys should all be paying attention to these early massive galaxies. They're really interesting. It's not obvious how they work in lambda CDM. This is a paper by Casey et al. In 2024, looking at data from the Cosmos Web survey. And basically the idea here is that this is the stellar mass of these objects and the redshift, and the volume of this particular survey is several times 10 to the minus 6. So if something has, this is sort of the rate of these objects that you would expect per volume. So this line corresponds to 1 in 10 to the 7 inverse megaparsecs of volume. So you would basically expect no objects above this line for that star formation rate in their survey, and yet they see these objects, right? So that there are these, at this high redshift, there are these surprisingly massive galaxies that are popping up. Right? And so in the paper, they make this statement that their presence, the presence of these galaxies here, demands either a higher abundance of massive halos at Z of 12 or an enhanced stellar baryon fraction of 0.2 to 0.5, implying star forming efficiency is elevated for a significant fraction of their star formation history. So those are kind of your choices. And as a particle physicist, I'm going to be focused on the former, whether we can get these halos. But obviously, it's an important question to ask the latter as well. Now, there are reasons why particle physicists, I think, step back and we're like, we probably don't have a lot to offer on that. And that is because our natural instinct here would be, well, let me come up with some kooky dark matter model with some kooky interactions, and that those kooky interactions are going to yield the, these interesting galaxies. But the problem with that is typically if you modify dark matter in such fashion that you can get these early galaxies, well, if I now get to integrate for billions of years after that, I get also all sorts of modifications to cosmology. And so there's a deep tension if your idea was to modify dark matter physics to say, I want to explain Z of 12, but I would like lambda CDM to explain Z of 0. And that's hard, right? It's hard to get stuff to act differently early, but then become normal. There was another paper that I think was very influential in lots of people's thinking about this by Sabti, Munoz, and Kamienkowski, where they said, look, we're going to tell you particle physicists just kind of settle down. And we're going to do the absolute minimal surgery that we can do to the primordial perturbation spectrum. So they said, look, we're going to amplify the contrast at a specific scale, almost a delta function, okay? So these are 3 different scales that they tried, and all we're going to do is we're going to just stick some extra power at one specific scale, specifically to get these galaxies, and then we're going to let the star formation rate be whatever it needs to be in order to get these things to work. So here it's a boost of 10, 4, or only 2. And then they said, all right, let's go now look at what the data tell us. And what they found is that if you use the JWST data, sure, yeah, it nicely would fit to these models, would happily give you the rates that you see. So this is the posterior of the number of galaxies that you expect as a function of the number of galaxies. But they would lead to such an excess of the UV luminosity function at Hubble that they would essentially be excluded. So when you take the Hubble UV luminosity function, you get a different posterior, and those things barely overlap at a very small amount. And their conclusion from this was that essentially you do the absolute smallest thing that you could possibly do to modifying your primordial perturbations, and all you're trying to do is fit these data. And what you get is too large of an excess in the UV luminosity function that would basically kill this. And so they say, look, I mean, I'm paraphrasing here. What they literally say is our analysis therefore severely disfavors a cosmological explanation for the JWST abundance problem. But really, what they're kind of saying is, if this doesn't work, then assuredly something more complicated than this is even worse, right? Because they've designed this to only get this. So let me come back to this picture and talk about how an event in the history of inflation might be relevant for early massive galaxies, whether they're in JWST data set or not. So here's the picture, right? So you're rolling down. I'm not going to color code it this time. You're rolling down. The horizon that you started with is getting bigger and bigger. You're getting little horizons inside there, so you're constantly living in one of these horizons, right? But let's now imagine that as the universe is expanding, something happens here. Okay? Most of the universe, nothing happens. But in one of these little patches of the universe, right, the universe is expanding and you live in one of these. And in one of those little patches of the universe, a bomb goes off. Something random happens. Okay? Well, then the debris field of that cosmological bomb will continue to expand as that universe expands. And so just like I said before, events that happen at some particular era of inflation get imprinted on a scale, on some specific scale, distance scale, in the universe that we see today. So if you can arrange for a cosmological bomb to go off, then the debris field of that cosmological bomb will show up in our cosmological data somehow today. And so the idea here is to set aside this idea of like basic Gaussian fluctuations, which is the usual story of primordial perturbations, that you've got some field that's doing nice Gaussian fluctuations, and you can categorize them all with 2-point statistics and maybe higher point statistics, and introduce the possibility of these cosmological bombs, of a Poisson process, something with very, very low probability, but sometimes happens. And the idea is that you might have these sorts of very rare stochastic processes in the early universe during inflation that might modify a region of our universe today. And these are different from the usual inflationary perturbations. We'll see that quantitatively in a second. But importantly, they're rare, because otherwise they would just simply be the perturbations. And because, at least as we're assuming it right now, they happen in a very particular era of inflation, they imprint their effects on a particular scale today. So let's start with the simplest model. Okay? The simplest model is not even a model. I'm just going to be a set of parameters. You say, look, at some point in inflation, something happens sometimes, somewhere. We're going to assume that what happens is that cosmological bomb, that rare event, increases the density contrast. So if you ordinarily, from inflation, expected a 10 to the minus 5 enhancement, maybe here you get a 3 times 10 to the minus 5 enhancement, or a 4 times 10 to the minus 5 enhancement. I'm not going to talk about really large inflations here. And it happens at some scale that imprints itself on the universe today, and it occurs with some probability. Okay, so not every patch has this happen, it just happens sometimes. Well, what happens with an enhanced perturbation? Well, we know that perturbations grow during matter radiation equality. We know they grow linearly until they become order 1 and then they collapse. If, in your mind, there's some characteristic redshift where perturbations collapse, and you now amplify those perturbations by some overall scale factor, those things are going to collapse at a redshift which is enhanced by precisely the same factor. So if you were thinking perturbations would ordinarily collapse at around z of 20, and now got an enhancement of 3, they're now going to collapse at z of 60, okay, just as a pick some numbers. Because they collapse earlier in the universe is much denser, and so their enhancement is now amplified by that factor of delta cubed. So if we're talking about a factor of 3, that's now a factor of 27, higher density. And there's going to be some specific mass scale that is actually relevant for these when these things collapse. These things, remember, have some physical scale. So there's the density inside that times the overall size of it at that redshift. So the final consequence of this is that you start with inflationary parameters of a density enhancement, a scale, and a probability. And what you end up with is the redshift where these things should collapse, the characteristic mass scale of these objects when they collapse, and the frequency that they appear in a co-moving volume. So this is just a parameterization. This is not a real model. This is just saying, let's imagine something happens. and let's suppose this parameterizes it. The point is that if something happens, rarely, during inflation and enhances density, the consequence of that is precisely a population of galaxies that form at a particular redshift of a sort of characteristic size early in the universe. So what's the real model? Well, the real model, at least the one that we talked about, was written by these authors in 2023, including Shobik. The idea is actually pretty simple. You don't need to pay attention to the formula at all. The idea is basically this. Inflation is happening, and there's the inflaton. There are a whole bunch of other particles out there. Maybe one of them, or some of them, have a mass which depends on the inflaton. Okay? So as the inflaton is rolling down, these things should get a mass which is changing. It's actually pretty common for this to happen. Indeed, usually particle physicists try to avoid this. Usually you end up with terms in your theory that wed the energy density of inflation times the masses of these particles, and they always end up getting these masses in particle physics which are actually large compared to the Hubble scale. The Hubble scale being an energy scale here. That's the one time I'm going to use it. So the Hubble, during inflation, is an energy scale and is sort of like a temperature. So if you have particles whose masses are kind of Hubble-ish, they might be produced rarely during the early universe. And so that's kind of the idea. So how did their model work? I mean, this is very schematic, but here is inflation. It's rolling down. Here is the mass of this other particle out there in the universe. As the inflaton rolls down, there's somewhere where its mass is minimum, and then inflation continues to roll, and its mass goes back up. And so if you think about a quantum process or a thermal process, the probability of having a particle produced is exponentially suppressed by its mass. And so the only time that you have any shot of producing particles is basically here. If it's way more massive or way more massive over here, you're not going to make it. Even here, it's going to be really, really unlikely. It's just the least unlikely point to make it. So as the inflaton rolls down, basically you don't produce any of these new particles. At this moment, maybe you rarely produce one of these particles, and then you roll down, and then again, you never produce these particles ever again. Well, as it turns out, these particles, when you produce them, act as a drag on inflation. They slow the field down, so the production of one of these particles precisely leads to this enhancement of densities that you see. And you can calculate the number density of galaxies that you would expect. Here are some random parameters we put in. And you see precisely this, that you end up with a population of galaxies forming at early redshift from these things that as time goes on eventually get swamped by the lambda CDM contribution to galaxies, and they become irrelevant. It's important that we have predictions, because if our prediction is everything looks like lambda CDM, that's not so interesting. But, whoops, that's not what I wanted to do. That's better. So you can calculate, for instance, the ratio of the lambda CDM prediction to the prediction in the new model, and that's this color-coded thing, the ratio here. So you can see in this plot here, redshift here, and stellar mass of the object here, that you can get very, very large enhancements of the number of galaxies. These orange lines are the lines for the JWST data. This is where lambda CDM would have predicted one galaxy, so more than one below here, less than one above here. This is in the new model, more than one below here, less than one above here. The blue lines are for a future Euclid survey, which obviously doesn't go out to such high redshifts, but will have good statistics and should have the ability to possibly test these large enhancements of galaxies at lower redshifts as well. So what's nice about this, again, is this is not a story that I'm telling my children, but it actually has predictions that we can test, and that if there are rare processes, if rare processes during inflation are actually manifesting themselves in the population of galaxies we see today, then we should see the implications in the future. It's worth going back, and maybe you're like, well, that's just fake and that's not interesting, I don't care. I think it's worth going back and actually asking the question, well, but what about Sabti, Kamienkowski, and Munoz, their paper where they said, look, we did this very minor thing of putting in these bumps to explain these things. Why was that not right? How did we get around that? And I have to say, when we wrote this paper, we originally didn't know. We were like, how did we get around that? Are we ruled out? Doesn't look like we're ruled out. And it turns out that it's because, and I find this funny, is that when you're a child and you take your first class on large-scale structure, you are told to write down a power spectrum and calculate all of your statistics from that. It's like the two-point function is the first thing that you talk about, right? There's no reason to talk about anything else. That's the smallest point function you can talk about. It turns out that when you have your Gaussian fluctuations, it is the right thing, but these Poisson processes are essentially only upward fluctuations. They are a contributor to the one-point function, right? You shouldn't even be thinking of this in momentum space. You should really be thinking of this in position space, but they're actually shifting the whole average up, but if you're calculating that on the top of a Gaussian background, it looks like a correction to the one-point function. And to me, it's just interesting is that like, I never would have thought, oh, I'm going to modify the one-point function. That would sound dumb. But that's actually what's going on in these models. And it's just an important lesson that sometimes our language, the way we even talk about the problem, sets us up for of not seeing answers that could be out there. All right, well, let me switch gears away from the monsters and talk about this. So I said that the amplitude of perturbations of inflation are related to the slope of the potential. And what if that slope changes? What if it's not going to give us 10 to the minus 5 perturbations? Maybe part of it's 10 to the minus 5 and part of it's enhanced to, in my case, I'm going to consider 10 to the minus 3. And it's important to notice that you can have a very abrupt change in the things that dictate inflation, whether in real life or in particle physics. So, so this is the idea. If the inflationary potential flattens, even for a period, the region of the universe that is sensitive to those perturbations will see enhanced perturbations on those scales. And if you actually go and you read papers, people talk about primordial black holes. They love primordial black holes. Can you explain some of the dark matter, all the dark matter, half the dark matter? Primordial black holes, a lot of the models, almost all the models, usually generate them in this way. That you have your inflationary potential coming down, and then you reach some region where the potential is extremely flat. And it's so flat, in fact, that you get these order 1 perturbations that generate primordial black holes. So in some sense, I'm considering those models, but I'm just lowering my standards to say I'm willing to consider perturbations which are much smaller than that. So the question then is, what if you have enhancements which are not order 1? What if I have an enhancement to perturbations which are important, that change it, but are not so big that we get black holes? Well, what do we know about primordial perturbations? So now I'm going to go back and talk about two-point functions after just saying how we shouldn't only talk about two-point functions. But here's the power spectrum of curvature perturbations as a amplitude of the power spectrum here as a function of scale. And we're thinking about primordial perturbations here. And we have great constraints from Lyman alpha and the CMB at these large scales. But at small scales, so sort of like megaparsec and smaller, we don't have a lot. The biggest constraints come from modifications to the spectra of the CMB. There's recently a paper that argued that there should be some dynamical heating from small substructures if they're present. But regardless, there's a tremendous amount of parameter space here where we really just don't know anything at these scales, where the perturbations could be significantly larger. And it's worth then noting that if indeed we don't know that much about this region of parameter space, that there are classic problems in astrophysics that are essentially small-scale problems. One of them being the origin of supermassive black holes. Supermassive black holes are massive objects. They're all over the place. From the outside, and maybe you can throw things at me for this, but from the outside, it certainly seems like there's a lot of discussion as to where they came from. Not to the point where it's not a settled question of like, yes, obviously lambda CDM in this particular way predicts that supermassive black holes could form. There's different scenarios that explain their origin, but I would not, to my sense, does not appear there's a simple consensus of where they come from. So my reading, again, of how it's supposed to work, right, how it should have worked, is that galaxies form around Z of 20 with stars. You get some seed that's sort of solar mass-ish, and then you grow via accretion. And the problem with this is that if you assume Eddington-limited accretion, there's only a rate of growth that you're going to allow for these initial seeds. And that's going to constrain your ability to get the supermassive black holes that we observe today. And if it were just about the supermassive black holes today, that would be one thing. But we go and we look at high redshifts, Z of 6 to 10, say, and you see these really massive black holes that look hard to get starting from stellar mass seeds. So this is a pretty famous plot by Bogdan et al. In 2023, where you have, in particular, this one particular supermassive black hole. And if you start with a solar mass object and you grow it through Eddington accretion, you miss it dramatically. So either, they state, you need super Eddington accretion, a sizable amount of super Eddington accretion to get to it, or you need to start from a seed which is much, much more massive. So if you're a dumb particle physicist, you say, well, why not just have heavy seeds? You know, that doesn't seem so bad. Just put in, you know, if you've got these black holes already, just make them bigger. Right? And of course, that's not so easy. And that's because gas clouds naturally collapse down to their Jeans mass. And if you have a very large gas cloud, it's going to, and you have a Jeans mass which is much smaller than that, then that large gas cloud will fragment into objects set by that Jeans mass. And if that Jeans mass is, 50 solar masses, then that's what you're going to get. You're not going to get a 10 to the 4 solar mass black hole. The reason why you get such a small Jeans mass, right? I can set up my parameters, sort of like characteristic densities of the universe, 10 to the 4 Kelvin, which is a characteristic cooling for atomic hydrogen. I can get a Jeans mass up at 10 to the 7 solar masses. The problem is that atomic cooling is not the story, right? The story is that atomic cooling will cool down to 10 to the 4 Kelvin, but molecular hydrogen is very efficient at cooling down to 100 Kelvin. So if I can have a much lower temperature, then I can have a much smaller Jeans mass. And if I have a much smaller Jeans mass, then these objects will fragment. So that's the problem, right? That's why you can't just be a dumb particle physicist and say, I'm just going to generate some really big overdensity and hope that it works, right? If there were only atomic hydrogen, great. Gas cools to 10 to the 4 Kelvin, and then isothermally contracts, and with a reasonable probability, you can get a black hole. But the universe is not made out of atomic hydrogen. There's a lot of molecular hydrogen out there, and that's the problem. Okay? So this was, at least from my reading, the motivation for considering this idea of direct collapsed black holes, which goes back a long time, including to people here. And the short story of this is that maybe you can get rid of the molecular hydrogen. Maybe, for instance, you have some nearby system with UV radiation which is getting rid of the molecular hydrogen, or whatever. You've got some scenario that gets rid of the molecular hydrogen, and if the molecular hydrogen is gone, then your only cooling process is from the atomic hydrogen, and if you only have atomic hydrogen, then you get down to these 10 to the 5 solar mass black holes. That's your Jeans mass, and you can get them, and life is grand, right? Maybe it's rare, but maybe it's enough to explain what you observe now. And then you can have these nice heavy seeds that just grow Eddington until you get to the objects that we observe. So that's already an interesting question, right? That was already an interesting question, understanding the origin of supermassive black holes. But it got even more interesting with JWST, because JWST has recently made a large set of observations of a population of objects that are called little red dots. And so now that I'm going to talk about little red dots, I finally have the opportunity. I'm giving a talk about JWST, and I get to put up really spectacular images from JWST. This is what they look like. It's a little disappointing, I got to say. But the objects themselves are not disappointing, just the images. That there are these populations of objects out there, these little red dots, that are quite ubiquitous. And they're funny, right? They're funny because if they're interpreted as is now, in like sort of increasingly standard interpretation, if there are black holes which are accreting, they're in an environment where the black hole to stellar mass ratio is very large, approaching 1, much larger than the sort of canonical ratio of stellar mass to black hole mass that is observed in ordinary galaxies. So if you're a particle physicist and you're looking at this, you're like, well, those actually do look like there's something new. They do look like there's something different. They don't just look like stellar mass black holes that then grew and did something interesting. They could be telling us something. So it's worth for us thinking about it. So this is the idea, right, including work by people here arguing that these are AGNs powered by these 10 to the 6-ish solar mass black holes, and that to get them, that you really are best explaining them by a direct collapse black hole origin, right? So they're in these all sorts of very, very strange features. And so it is being argued that, not by me, but by others, that this is really strong evidence for these as being some very broad population of direct collapse black hole accreting in the early universe. So then you can ask the question, where did these seeds come from? And that comes into where we come in. Primordial black holes you've probably heard of. We talk about this idea of something we call not quite primordial black holes. Wenzer came up with that name. I thought it was great. So primordial black holes are the ideas that you start with perturbations in the primordial power spectrum, which are order 1, so 0.1 to 1. They're so big that they cause the universe to collapse almost right away, and you get a black hole because the curvature is so strong. But like I said, it's actually sometimes quite hard to get order 1 perturbations, right? If you can get order 1 perturbations, then you can get 0.1 perturbations, or you can get 0.01 perturbations, you can get 0.001 perturbations. So you can ask the question, what if I consider all those models, but instead of getting these huge modifications, I get somewhat smaller modifications, okay, that don't collapse right into a black hole? Well, we know that these perturbations will grow logarithmically during radiation domination, and they grow linearly during matter domination. And so if you have a large enough density perturbation, so here are just a few different characteristics. So you can start with a sort of conventional perturbation on different distance scales, and they will grow and collapse here. This is a function of redshift here, so they collapse, in the universe today. But if I start with an enhanced perturbation, say here this is 1 at 10 to the minus 3, here's 1 at 10 to the minus 1, these perturbations will grow, and in this case, collapse. This one here collapses at a redshift of 100. This one collapses really, really early, and you get a primordial black hole. But this one collapses at some redshift of 100. So you can ask the question, well, didn't you just spend all this time telling us that making some big overdensity of dark matter that collapses is pointless, right? Didn't we just go through this whole thing about molecular hydrogen being out there and that it doesn't really buy you anything to have some big overdensity that collapses? Well, it's interesting, because if you actually look at the history of the cosmological history of molecular hydrogen, you find that molecular hydrogen wasn't always around. That's because just the CMB is hot enough to dissociate molecular hydrogen efficiently in the early universe. And so here's this paper by Hirata and Padmanabhan in 2006. There's newer ones that are even better, but they have the nicest plot, and that's why I'm using it, where this dark black line is their density of molecular hydrogen as a function of redshift. And you can see you start from a very, very, very low fraction of molecular hydrogen, and you really only kind of get to the amounts that we have today after redshift of 100 or so. Okay? That's the only place where it becomes efficient. So then you can ask the question, okay, and this is, I think, not a brilliant observation at all, but you can say, well, if this molecular hydrogen is bad and causes my gas clouds to fragment, what if I have overdensities that collapse early on before the molecular hydrogen has had a chance to form? Well, if the molecular hydrogen is not there, I should have no molecular hydrogen cooling, and I should have just atomic cooling, and these things should not fragment, and they should indeed collapse into some order 1 fraction of the time direct collapse black holes. Right? So in some sense, if you want, the only point here is to make the observation that we've had this tremendous literature on direct collapse black holes and understanding their process. There's numerical simulations, all these things. And our point is simply that, hey, if the ingredient that you need for a direct collapse black hole is an overdensity and no molecular hydrogen, well, if you just put in a slightly enhanced overdensity, you get both of those things for free or together. So you put in some overdensity, which is something like 10 to the minus 3. It grows, goes nonlinear, and collapses before molecular hydrogen is present in the universe. It will not fragment, and you will get precisely these sorts of things. You do have to be a little careful You can't just apparently write a paper by saying that. You have to calculate something more. So you can actually calculate the formation rate as these things are collapsing of molecular hydrogen in these systems and ask, do they make so much molecular hydrogen that they will then cause themselves to fragment? And when you do it a little bit more carefully, we find that actually, as long as these things collapse by about redshift of 200, you do not get too much molecular hydrogen and they will not fragment. Now, 200 is probably conservative. You could probably go a little bit lower than that, but 200 looks safe to us. So this is the basic idea. You have some initial overdensity, something like this, higher than the standard cosmological perturbations. They then grow to order 1, trapping baryonic gas inside of them. That baryonic gas then cools through this atomic cooling mechanism and collapses a la direct collapse black hole, except for now we have a nice origin for these direct collapse black holes. So you have a particle physics way of explaining an origin for these seeds. So you can kind of ask about where these things can happen. So this is the amplitude of the initial perturbation, not the power spectrum, but just you give me a perturbation of a given size versus a wave number. This curve here is you need to collapse by z of 200, so anything above here collapses. This line here is that the virial temperature of that object is 10 to the 4 Kelvin, so that you can actually cool through atomic hydrogen. So this region here looks to us like the region where this sort of thing should happen. And so then we can go back and we can ask, well, is this something that then can explain the little red dots? So we go back and we put in 2 basic models, one which is a step function, one which is a Gaussian quasi-delta function, and just ask, not because these are the most motivated models, although they're not that hard to get, at least the step function is not hard to get, and ask, can we get a population of primordial black holes that are consistent with these little red dots? And the answer is yes. That this kind of enhancement to the power spectrum at these scales would have precisely this sorts of consequences. So great, if you have these enhanced density perturbations, they should collapse, but do they? That's the question. But again, the difference between science and what we tell our children is evidence, and what's interesting is that there should be a tremendous difference in signals between black hole seeds that form at z of a couple hundred and things that form at z of like 20. Right? You've got accretion, ionization in the early universe, all sorts of things that are going on that we're currently studying to understand what the implications of, and I think it's actually just kind of cool, because before this, you never would have thought, oh wow, can you get a black hole forming at redshift 300? Well, as it turns out, it looks like you can. But we don't yet know the implications, but there's clearly a lot to think about. So let me conclude. I'm excited about all these modern cosmological surveys and experiments that are telling us about the z equals 10 universe. The universe was complicated then, but not as complicated as it is now. And as a consequence, it really is this interesting place where we can ask different sorts of questions and test them. Adding to that, we've already seen surprises, right? We are in a crisis of cosmology, or starting to be. And those surprises make you think, could this be something which is beyond lambda CDM? And it's worth thinking about that. Because even if we're wrong, we come up with scenarios that might be relevant for other things as well. But what we found is that, to me, from a particle physics point of view, very, very pedestrian modifications to the physics of inflation. They can grow and collapse and yield surprises in the high redshift universe. These are not dramatic changes, random particles whose masses change during inflation, a change to the tilt of the inflaton potential. These are not big things. These are small things, and yet they lead to big consequences. And in particular, that they yield possible direct collapse seeds for direct collapse black holes and early massive galaxies consistent with existing observations. Is that the explanation? I don't know. But I think that it's clear to me anyway that there's a lot to be learned about particle physics, not just astrophysics. And so I'm excited. I think that the situation is exciting. I'm looking forward to seeing what happens. Thank you.
Okay, I see it's 2:30, so some people might have to run. We won't take offense, but Charlie has a question.
So this is the third point here. The third point, I mean, I don't know anything about inflation, but how do you connect these, mild changes to like something physical? Like what does it mean, or how do you get these changes?
You mean in the model?
In the world, ideally.
Well, I don't know exactly what you're asking.
That's
Here's
right. I don't either. But
what I can say is that the thing about inflation. Okay, I'll just say some things.
please.
The thing about inflation is that people spent a long time trying to understand inflation because the reality is in a generic particle physics model, scalar fields do not want to do that. That is not something they want to do. They do not want to have a large amount of energy density that sits there and slowly rolls as the universe expands by e to the 60. Okay? So people flipped over themselves and tripped and bent backwards trying to do all sorts of scenarios where you could have the physics do that. And the reason, of course, we've tripped over ourselves to do that is because we look around and we're like, it sure looks like the universe expanded by a lot, so the universe is telling us that it wants to do this. But to the point I make is just that it's clear that our idea of what's generic physics is not what is happening in inflation, because inflation clearly happened, and that's not what we would have guessed at first principles, right? On the other hand, if you do get some stretch of inflation, then it will expand the universe, and it will become really, really important, right? So you don't have to have inflation be everywhere in the landscape of that model. It just has to be somewhere in it that for some period of time that inflation can happen in this kind of like nice controlled fashion. But all we've tested is that inflation happens in this nice controlled fashion over some narrow region of scales. Almost certainly outside of that region, other things happen. Whether these things happen is an open question. But the point is that it's very, very unsurprising. Oh, I didn't put in my JWST images. It should not surprise us if you look at large enough scales. It's almost like lambda CDM. We talk about dark matter in CDM. Everybody believes that at some point it's not CDM, not to every single limit. It's just a question of where it stops being CDM, right? Some scale, some interaction, something is going to tell us where it deviates. And maybe it's relevant for cosmology, and maybe it's not. But somewhere it stops. And I think the same thing is true for inflation, that somewhere in there, other things are going to happen. Whether they're relevant for cosmology is a separate question. Those are words. I don't know if I answered your question, but I answered a question.
Thank you. So you talked about kind of like a rare stochastic process as Poisson thing. So, and then you mentioned how, you're most going to probe like the depth of that potential where that rare process is most. So does asking how common are these perturbations, how common is a little red dot, that sort of thing, does that tell you something about the relative energy scale? And is that interesting?
So it does. In any given model, I don't know if this is going to be a very satisfying answer, but in any given model, normalizing to any observation is going to fix that amplitude. Yeah. And then there's a separate question, which is that consistent with things that we've already seen? And at least to me, what's interesting is that, indeed, you can understand little red dots specifically by a modification to the slope of the inflaton potential. And again, I don't even know. Let me take one small step back. I'm talking about a modification of the inflaton potential so that I can say, here is a not crazy model that does this. But there are a lot of other scenarios that can do it as well. Lots of other models. People have models of axions that when the axions start rolling, they lead to really large isocurvature perturbations that would do the same thing. You could have some subcomponent of dissipative dark matter that collapses and generates these overdensities. I'm giving you one specific model. To me, kind of what's interesting is that if you have any model that can amplify the perturbation from 10 to the minus 5 to 10 to the minus 3, you're going to get, and it's at the scales that we're talking about here, you're going to get the origins of some population of direct collapsed black holes. And at this point, the things we've looked at have all been consistent with existing data. But it's not just this model. I put in a model because if I don't have some model, then it's like, well. But it's actually, I think, a very, very common scenario where that people have changes to the power spectrum at small scale. Sometimes it's suppressed, sometimes it's enhanced. I've seen models with both. If you get an enhancement, then this is going to be a consequence.
Last question.
So in this scenario where you have Poissonian events during inflation that don't impact the 2-point statistics but impact 1-point statistics, how would that imprint itself on, say, a very futuristic 21 centimeter survey where you do the H1 to Redshift 50?
I don't know. I don't know. I don't know.
And with that, we'll end.
Yeah. I don't know. I'm sorry. We're thinking about 21 centimeter in the context of the direct collapse black holes. We've not thought about it in the context of these Poisson processes. It's been looked at in the CMB, and in the CMB, it seems too rare. But of course, that's a different scale. They looked at it for different scales. So they didn't find any evidence for it. These scales would not appear in the CMB if you're trying to explain this. But I don't know. Sorry.
I think there were other questions. Come on up and chat with Neal, but we'll let the crowd go for now. Let's thank Neal again.